Hi, welcome back. Right now, we'll actually learn on the pipeline system design. So, the previous part, the part one, we have learned on Bernoulli's equation. Okay, v squared by twice g plus z plus some head loss. Okay, equal to constant. Okay, so that is the Bernoulli's equation we have learned, and for this head loss or h F, okay, head loss due to the friction, we know how we can calculate the head loss due to the friction. To get the head loss due to the friction, we got to calculate the friction factor. We also have to know the equivalent length of the pipeline, and to calculate the friction factor, we need to calculate the Reynolds number, okay, and also the relative roughness. And when we actually calculate the relative roughness, we get the Reynolds number using the Moody's chart, okay, using the Moody's chart, which is F versus R, so, and that relative roughness. So based on that chart, we can actually obtain F. Okay, now at this session we'll actually learn how we calculate the equivalent length, and also how we can actually design the pipeline for oil and gas systems. Okay, so let's learn. Now back to the friction loss. Okay, remember this friction loss here we have discussed. So this friction loss, at the previous lecture, if you see the equation for the friction loss, we actually used the Darcy-Weisbach equation, and there's this friction loss we actually calculated through the Moody's chart. Okay, from the Moody's chart we got the friction factor. However, except for using the Moody's chart, like the Darcy or Moody's friction factor, we also have different types, different ways we can actually calculate the friction factor. Okay, one of the ways to use the Colebrook-White equation, and this Colebrook-White equation gives a better correlation with the field data when it's applied to the crude oil pipeline. So remember, when you actually use when you actually design for a crude oil pipeline, you got to use the Colebrook-White equation, and as you can see, this is a very complex equation. You have to use the iterative method, that means the Newton-Raphson method, or any types of iterative method for solving the equation. Okay, this should be determined by the iterative process. Okay, so this is about the Colebrook-White equation, and there is another one we called Hazet-Williams equation. Okay, remember at the part one we have said, like, there are several ways we can actually calculate the friction loss, like the Darcy-Weisbach equation through the Moody chart. Okay, and this Hazet-Williams equation for the crude oil. Okay, and there is another one, the Colebrook-White equation. And this Colebrook-White equation we can calculate for the pressure drop for the refined petroleum. Okay, now this Hazet-Williams for the refined petroleum. Now Colebrook-White is for crude oil, C for C. Okay, that's how you can remember it. But the Hazet-Williams is for refined petroleum. That means this is the equation for the Hazet-Williams. Now why is that? Because you can use the Hazet-Williams equation for refined petroleum, but you cannot use it for crude oil or heavier liquids because of the viscosity, actually. Okay, so this is for the low viscous fluids. Okay, but this is the equation for the high viscous fluids. Okay, so that's exactly why we should use the Hazet-Williams equation for the refined petroleum. For instance, what? Gasoline, octane, okay, kerosene. So for these we can use this Hazet-Williams equation to calculate that. Now what are these terminologies? LE is the equivalent length, we know what is that. internal diameter, Q is the flow rate of the fluid, C is the Hazen-Williams factor. Okay, so at the previous one, the Darcy-Weisbach equation, we had the friction factor, but here we have this Hazen-Williams factor, which is also a dimensionless amount, and CF is the conversion factor. For imperial unit, it's 4.72. Okay, now this C, Hazen-Williams C factor, is a number based on experience with a particular product and the pipeline. Okay, for an example, one product pipeline company may use C125 for diesel and C150 for gasoline. The higher CR factor, the higher will be the flow rate through the pipeline, and lower pressure drop due to the friction. Okay, remember this important. So how can we actually calculate, or how can we actually evaluate the C factor? So this is the chart. Okay, so this is the chart we can actually calculate the C factor from. You probably have remembered this chart when we were actually calculating the roughness. You have seen there's the C factor. Okay, so unlike Moody's diagram or Colebrook-White equation, Hazen-Williams equation does not use Reynolds number, okay, or the viscosity of the liquid to calculate pressure drop, and that's exactly why we have this factor. Okay, now this factor loosely based on this roughness actually. Okay, so for instance, steel pipeline, okay, the carbon steel pipeline, these are the C factor. That means, like, I mean, for low it will be 80, high 150, but optimum is, like, I mean, 100. Okay, so that's actually explained in here. Okay. So this is how we can actually calculate the Hazen-Williams equation, and then we can plug in all the things, and then we can actually calculate the HF from the data. We'll actually see how can we do that. Now let's talk about equivalent length. Or the minor losses. Okay, so these are the major loss. These are the major loss we calculate, like the pipeline frictions. How can we actually calculate the minor loss? Let's see that. So minor loss are those friction losses from the fittings, valves, entrance, and exit losses. Okay, so these are the three different ways you can actually calculate minor loss. One is the resistance coefficient K, equivalent length method LE. We know about this. We'll actually see more. And flow coefficient CV. Okay, now this is how we can actually calculate through the resistance coefficient. So the minor loss HF equal to K times V squared by twice G. Now the friction head loss through the fittings, the resistance coefficient K is known. That's how we can actually calculate. Now for different types of fitting and different size, we have these K values. Okay, so we can actually calculate the K values with that. So this is the L by D and this is the F. So K is the function of L by D. Okay, so there's a little difference in the K values for different scheduled pipe fittings. It is sufficient to use data for the 4D schedule 4D pipelines. Okay, so we will just use the schedule 4D. This is most commonly we actually use for the schedule 4D pipelines. Now let's see how we can actually determine the K. So how we can actually calculate the equivalent length. So the equivalent length, or LE, is equal to K by D of F. Okay, so this is how we can actually calculate the equivalent length. So the head loss due to the friction represent in length unit. Okay, and the conversion developed to describe minor losses simply as the equivalent length of the straight pipeline. How is that? Just imagine one thing. I mean, let me quickly give you one example. For instance, you have a pipeline and you have a valve. So the friction loss, or like the major loss for this pipeline, is, for instance, HF equal to 2 feet. Okay, so the major loss is accountable for this pipeline. Okay, now what's about this one? How much loss a valve can have? Now the way we actually calculate it, we convert this valve loss, like loss due to this valve, the pressure loss or the friction loss due to the valve, to an equivalent length of a pipeline. Okay, so for instance, this is 1 feet. That means the pressure loss, the friction loss caused by this valve is equivalent to 1 feet of the pipeline's frictional loss. Okay, so the total HF would be 2 feet, which is the major loss, plus 1 feet, the loss due to the valve, that means the minor loss, so total 3 feet. Now the pipeline's length is not 3 feet, or not even like the loss. Okay, so this is not like the pipeline's length. However, we just calculated 3 feet. We actually make an equivalent length for this unit. Okay, so this is how we actually calculate the the equivalent length, and this is the conversion chart for the equivalent length. Okay, so let's do a problem, then we can actually easily understand how we can do that. Okay, so the problem is find the total pressure drop. Okay, so what is the problem definition? One Mpsh 18-inch diameter pipeline, that means the pipeline diameter is 18-inch, right? Anything above Mpsh a certain value is more than it, so that means Mpsh 18 is equal to the Mpsh D equal to 18-inch, or 18 by 12 feet. And the wall thickness is this. That means how can we determine the internal diameter? So ID would be 18 minus 2 times 0.375. It's total inch divided by 12, right? So this would be the total internal diameter. And it got 5,000, it is 5,000 long, 5,000 feet long, and it got 6 elbows, 1 globe valve, and 1 gate valve. Use the Hazet-Williams equation with a C factor of 140 to calculate the total head loss due to the friction, and the flow rate is 10 cubic feet per second. Okay, so now let's calculate. We know the Hazet-Williams equation. This is the Hazet-Williams equation, right? So what are the unknowns? The Q, C, L, E, T, and see if it's a conversion factor. So here, and the first thing, we need to calculate the LE, or the equivalent length, and then we get to calculate the we know the C, we know the Q, and we know the D, so we can easily calculate the HF using Hazet-Williams equation. Okay, so using this formula. Okay, so let's calculate the total length, like the total equivalent length at first. So what are the items we have? We have a straight pipeline of 5,000 feet. We have 90-degree elbow. We have gate globe valve, and we have gate valve. So if you check here, we have 90-degree elbow. Okay, bends. Here is the elbow, 90-degree elbow. We have we have a globe valve. What is a globe valve? It's a globe valve. We have gate valve. Okay, and we get straight pipelines. Okay, now let's do the solution. So let's organize a table to list all the pressure drop items, and then we can calculate the equivalent length according to the table for Mpsh 18 inch. The straight pipelines quantity 1 5000. So 5000 times 1 equal to 5000. Okay, 90-degree elbow, how many we got? 6. Now for the 90-degree elbow, okay, for schedule 40 nominal pipe size, Mpsh 18. Here is the Mpsh 18. This is Mpsh 18, right? So we are interested on this chart. So 90-degree elbow, where is 90-degree elbow? Here. Sorry, as you can see 42.4 here. I mean, when it says 90 degrees elbow, it's always short radius, not a long radius. Remember that. 42.2, right? So we write down 42.2. So 6 times 42.2 to 53.2. Okay. We got globe valve. How many? 1. And what is the unit for the globe valve? Let's see. This is globe valve. The K value is 478. 478. 1 times 478. 478. We got gate valve. How many gate valve? 1. And the value is 11.3. 1 times 11.3, 11.3. So total, so this is the original length of the pipeline, and these are the equivalent length for all of the pipeline, all these equipments. Okay, so all these pipeline fittings. So what will be the total length? So it's 5742.5. That means this 742.5 feet is the equivalent length of the pipeline. That means, for instance, we have pipeline with 6 elbow. That means it was like bending, like for instance like this. Okay, and we have one globe valve, we have one gate valve. Okay, and that's the, for instance, that's the original thing. So that means the length of this pipeline is total, like the straight pipeline total is 5000 feet. Okay, and for these 6 elbows plus this globe valve plus this gate valve, we have another 742.5 feet. Okay, so total equivalent length would be 5742.5 feet. Clear? I think it's really easy to calculate, right? It's really easy. You'll just go to this chart. From the chart you can actually calculate it. You remember, like when we were actually talking about the valve at the module 3, I believe, yeah. So module 3 or module 2, I think module 3. So there we have, I mean, I've told you that the globe valve got more pressure drop than gate valve. Now we can see the globe valve, the pressure drop got more than the gate valve, right? So anyways, this is how we can actually calculate the LE, or equivalent length of the pipeline. Remember? Now we got the LE. We know how to calculate D. Okay, and we got the Q. We have C. Okay, and the CF is 4.72 because all these formulas are in the factors. So if you use the American Engineering Unit, you will just use 4.72 as a conversion factor and put all the informations. We got total head loss 34.96 feet. Okay, easy and simple. right? So this is how you can calculate the pressure drop, like the head loss due to these using the Hazen-Williams equation. And the part 1 we have learned to calculate the head loss using Darcy-Weisbach equation. Okay, so remember. Now sorry, now let's talk about pumps at this section. So the last module we have discussed about the pump, and we have discussed lots of things about the pump, really. So you remember, like at the earlier we when I was actually explaining you the Bernoulli's equation, there is the terminology we have. It's like head added by the pump. Okay, so pump act as a booster. Okay, so pump increase the pressure of a fluid. So how much pressure a pump can add, so that's we'll actually see in this section. Okay, so the pump can add this amount, and that's we call the total suction head of the pump. Okay, and what is the total suction head of the pump? How we can actually define that? Total suction head is Z1 minus Z pump minus HF suction plus P1 by rho. What are these? These are, Z1 is the elevation of the level of the liquid to be pumped. Z pump is the elevation of the pump impeller to the center line. That means, for instance, here you have the pump, here is the liquid, okay, and you are moving the liquid in here. So what happen if this is the ground? So this one is Z1, sorry, so elevation of the level of the liquid to be pumped. So this is the ground, for instance. Okay, so this is the Z1 and this is the Z pump. Okay, and this is the base ground. Okay, and H suction, this is the head loss due to the friction for the entrance loss, and P1 is the pressure at the level of the liquid to be pumped. Okay, so this one is the P1. So this is how we can calculate the total suction head. Now, what is the total discharge head? So this is HS. What is the total discharge head? Total discharge head defined that Z2 minus Z pump plus HF of discharge plus P2 by P1. And what is Z2? Z2 is the here. Just 1 second. So the height of the pump at the point you actually want to weight it, and HF is the head loss in the discharging of the pipelines, and the total dynamic head we calculate TDH is equal to suction plus discharge, total suction head plus discharge head. Okay, so you remember the Bernoulli's equation HA that I just showed you, that is the TDH. Okay, when there is no loss, head loss of pump via impeller, and the velocity head is ignored. Okay, so HA at these equations, at this Bernoulli's equation, here here this HA, this is the addition of total suction head plus total discharge head, or we call it TDH. Okay, remember that. Now, power requirement. So probably at the section 3 you already have learned that we need a specific power, and we have seen this graph. Okay, so how much power it would require to draw the pressure. So what is the formula? Formula is bhp, or break-even horsepower, equal to the the flow rate. GMP is the gallon per minute, the flow rate of the fluid. TDH is the total dynamic head. We calculate it in here. Okay, SG is the specific gravity of the fluid. This is just the unit conversion factor, and eta is the pump efficiency. And usually the pump efficiency is 70%. Okay, so this is how we calculate the break-even horsepower. Mpsh, net positive suction head. So a fluid at a lower pressure, it may be vaporized at the suction, and it could destroy the pump impeller. What is that? Do you know, for instance, water, okay? Water also got some air bubble dissolved in the water. So it's not only water. In crude oil, we got methane. It's dissolved, okay? At a certain vapor pressure, is water can release the air bubbles, or this crude oil can release the methane, and when the impeller of the pump, it is a centrifugal pump, the impeller actually rotates very fast, right? And these bubbles can hit this impeller and it can destroy the whole pump. Okay, so we have to make sure the pump don't go at a certain pressure, and to avoid, we should avoid that certain pressure. Okay, so a method for determining whether or not a pump will be prone to cavitation relies on comparing the net positive suction head required to the net positive suction head available. So if net positive suction head available is greater than net positive suction head required, that means NPSHR, the required is less than available, then there will be no cavitation. Okay, and how can we calculate that? We should check NPSH equal to HA minus H of VP plus H of ST and F of suction. What are these? So NPSH is equal to absolute pressure head. Okay, for open tank it is atmospheric pressure. Okay, vapor pressure of the liquid, static pressure, and the suction pressure. If we know all this information, we can calculate NPSH, or net positive suction head. And after calculating the net positive suction head, if we check and if we see it is more than the net positive suction head required, or the threshold value, then we are safe. But if it is less, then we should be aware of the situation. Okay, we should avoid the situation. Now let's see a math how we can actually calculate the NPSH. For instance, we install a centrifugal pump. Okay, a centrifugal pump is installed where the liquid will be pumped out of a storage tank, which is located at an elevation of 25 feet. So this tank head is on the elevation of 25 feet above the center line of the pump. So this is the center line of the pump. Okay, the piping from the storage tank to the pump suction consists of the pipe of, this is the absolute roughness, the valves and fittings. Okay, we should calculate the NPSH. The flow rate is given and the specific gravity is given. Okay, and the viscosity is also given at 164 degrees Celsius. Okay, so here is the relationship between the vapor pressure and the temperature and density table is also given to us. Okay, now let's do the math. So what are the information we have? We have HA 33.9. We know that, okay, because you remember for an open tank, it's written it's an open tank and it is same as the atmospheric pressure. Do you know that at the atmospheric pressure, 1 atmospheric pressure is equal to 76 centimeter of mercury? Do you know that? We know. Now, what does that mean? That means, like, if you have a mercury in a tube with this diameter d, okay, for instance, this is the mercury you have, and you have an open tube of this diameter d, and from earth ground to the earth total atmosphere, for instance, this long atmosphere, several thousands of miles long, this atmosphere, the whole weight of this air from earth's surface to the upper atmosphere, okay, the total weight is equal to the weight of mercury of this 76 centimeter, the tube, okay. So in a tube of 76 centimeter high, the total weight of the amount of this mercury is equal to the air weight. That's a kind of like a work as a kind of like a balance, okay. So mercury one side, air another side, air and mercury is equal, like that. Now if you replace this mercury with water, okay, then you need 33.9 or 34 feet of the length of the water is equal to this air, okay. So that's why we said at the atmospheric condition, this air length, I mean the water length would be 33.9 feet, okay. That's how it came. All right. So the vapor pressure at 167 degree Fahrenheit, how much would be the vapor pressure? 167 degree Fahrenheit, 167, the vapor pressure. This one, like, how much? 12.9. So static pressure equal to Z1. You remember how we calculate the static pressure through this formula, okay? Z1 minus Z pump plus tank head. Tank head is 25 here, 25, okay. So we got static pressure 30 feet. So how can we calculate the Mpsh? Mpsh equal to HA plus HVP. We know HA, we know HVP, we know static. Now what the things we need to know? Friction loss, friction head loss in suction piping from the tank to pump. So in order to do that, we need to calculate the Reynolds number, okay, and here we got the Reynolds number, which is 43,000, and we got to calculate the pipe relative roughness because this information is given already. What is the pipe relative roughness, okay. So we got this value, and using the Moody's diagram we calculate the friction factor, okay. You should actually do it by your own hand. That's how we know how to calculate the Moody's diagram, right? So, and how can we calculate the velocity? We get the flow rate divided by area, we get the velocity, which is 5.44. So if we use this Darcy-Weisbach equation, and then we can calculate the HF suction, okay, the suction head, and then in PSH equal to HA minus HVP plus HST minus F of suction. That means we get the in PSH, okay. Clear, easy and simple. So All right, folks. So this is all about today's lecture on the part 2. And we have learned how to design a pipeline, how to calculate the pressure drop, and how to calculate the pressure drop from the pipeline system design, and which is a very important part of designing a pipeline system. Okay, so the next part we'll learn on the petroleum facility design. Stay with us.